4.2 Approximation techniques. The approximation technique here is called linear approximations. So this is a way of approximating the value of a function, knowing the derivative at a different location. I'll try to draw a picture to demonstrate what this is about. And there's x. We got some function, f of x. Let's just draw it something like this maybe. Okay. So if we know the value at some location, I'll call it a. So up here we have a comma f of a, of course. And that's a known value. And if we should move somewhere away from a, I'm going to move to the right. It doesn't really matter which direction. So I'm going to move to the right a little bit. And it's such a little bit, which is kind of important to this whole procedure here, that I'm just going to call it delta x. Okay? So a, and I shift down a little bit here. I'm going to exaggerate the distance here just to make the picture clear, hopefully. I'll move it all the way down here, and we'll call this a plus delta x, some change in x across here. So that distance is, of course, delta x itself. All right? And we map this up to the curve. And this would be a plus delta x, comma, f of a plus delta x. Okay, so this is the value we don't know. This is the value in question. We want to try to figure out a way to approximate f of a plus delta x. Okay? So that's our goal. And the tangent line, i.e. the derivative, will come into play here. Approximate f of some value further down. Okay? But again, it's not much further down for a reason I'll explain in a moment, otherwise the approximation won't be very good. So we can construct the tangent line at A. There. Something like that. All right. So if this is the tangent line in red, then the slope of the tangent line is, of course, dy over dx, which means that this ratio here, the ratio of the rise to the run, you might say, should be dy to dx, right, for our tangent line. This point here is going to be our approximate to this location, to this height here. Now, right now it doesn't look like a very good approximate because I've exaggerated the whole picture, but really the tangent line would be quite close to this location, as long as we don't stray too far away from A. Okay? So let's construct the tangent line in abstract here and see what we come up with. So we know that the slope of the tangent line is dy dx should be f prime at A, right? It should be the derivative right here at this location. That's what's generating this slope for this red tangent line. So the slope of the tangent line is dy dx, and that's why dy is the rise here and dx is the run here for the slope of this red line. But we know it's going to be the value f prime at A. Once we know f, we of course know f prime, and we can plug in the value A to get this particular result. So to construct the tangent line now, it should be that the tangent line itself should be the variable y minus the function location here, f of a, equals the slope of the tangent line. So that'd be f prime at a. This is something you've done many times, it's just I'm doing the abstract now. And then we'd have x minus the value a here, right? The x coordinate here, x minus a. Okay. So solving for y, to write the tangent line in the usual way, we would have y equals slope times x minus a plus f of a on the right hand side. So f prime a times x minus a plus the function at a. Okay, so this describes all of the heights along this curve here. All right, when I say curve, I mean the tangent line. Right? A line is a curve as well. So all the points along this line, along this curve, the red curve, are going to be described by this representation down here.